DiffusionLight, light probes for free by painting a chrome ball. In this paper, we aim to estimate the lighting condition in an input image, which we represent as a 360 HDR environment map. So, how do we solve this task? If we could somehow place a chrome ball in the scene during image capture, we'd see the environment in its reflection, an idea dating back to the 80s. Our work shows we can simulate this by in-painting with a pre-trained diffusion model. Turns out, this idea works surprisingly well. However, when we first tested this idea, none of the diffusion models, including those designed for in-painting, could do this reliably. State-of-the-art models like Stable Diffusion XL sometimes produce a disco chrome ball, or multiple balls, whereas commercial products like Firefly and DAL-E2 often reconstruct part of the Taj Mahal back without producing a ball. Paint by example and IP adapter, designed to imitate a given reference image, sometimes fail, or produce poor results. In contrast, our method consistently produces a reflective chrome ball that perfectly fits the circle mask, captures the lighting, and includes convincing details. Besides a technique to reliably in-paint a chrome ball, we also propose a way to produce an HDR ball using stable diffusion trained on regular LDR images. Our approach stands out from recent work in this field, which typically trains again conditioned on various feature maps from the input, such as EM-Light and Everlight. Other works reframe this problem as image-out painting. Immerse GAN generates HDR maps directly from a text-conditioned GAN, while OmniDreamer first predicts a low-resolution map, then refines it to improve quality and resolution. Following the out-painting idea, state-of-the-art StyleLight uses GAN inversion to transform the input into a latent code, then uses that code to generate the HDR map. One common limitation among these methods is their reliance on HDR 360 datasets, which are small and not very diverse, compared to the billions of regular images on the internet. Our work targets real-world captures beyond those 360 datasets, such as macro or bird's-eye view shots, non-photorealistic styles, or basically any kind of image. Our pipeline builds on a standard stable diffusion in-painting pipeline, which takes a chrome ball text prompt and a location mask as inputs. The first modification we made is to condition the SDXL with a depth map via ControlNet. The depth map is predicted using an off-the-shelf estimator and includes a white circle from the in-painting mask. While this conditioning helps the ball consistently appear and fit the mask perfectly, the balls still look quite random, similar to the results from other models. However, we noticed that the average ball roughly captures the light direction. So, our key idea to improve quality is through sample averaging. Specifically, we first generate N balls and compute their median, which is then used as the starting point for generating a new chrome ball. We do this by reintroducing some small noise to this median, then denoise it again using the same pipeline. This technique is also known as SD-edit. We can vary the seed, and produce a new set of balls from this median. Then compute another median. This process can be iterated multiple times. Here we show the results when starting from 4 different noise maps. You can see that the light estimation becomes more accurate as we repeat the process. Now that we can generate high-quality balls, the next challenge is to make them have high dynamic range. We found that, even though Stable Diffusion was trained on LDR images, it still understands HDR and the wide range of real-world luminance. This is evident from our experiment, where simply adding black-dark to the prompt reduces the exposure, bringing out the sun's round shape. This finding led us to the idea of exposure bracketing to achieve HDR, but we still need a way to condition the model with specific exposure values. Our idea is to fine-tune Stable Diffusion using LoRA to map these two prompts to specific EVs, chosen to be 0 and -5. These training balls, about 1,000 in total, are synthetically generated using text-to-light. Our training strategy also allows us to interpolate the embeddings of these two prompts and generate balls with any exposure value in between. Using this LoRA, we generate balls with various EVs, then merge in the luminance space, while taking the chroma from the EV0 ball to minimize ghosting artifact. We compare our method with StyleLight, the state-of-the-art, on Laval indoor dataset, which StyleLight was trained on. Following a standard protocol, we render mirror, matte, and diffuse balls under the predicted HDR maps and compare them to the ground truth. Our method significantly outperforms StyleLight in angular error and normalized RMSE and remains competitive in scale-invariant RMSE. For outdoor scenes, our method still produces good results while StyleLight doesn't quite work and would require retraining on outdoor scenes. Although retraining StyleLight on more kinds of scenes is possible, gathering 360 maps for these in-the-wild scenes is nearly impossible. In contrast, our method works out of the box. Our chrome balls can reflect various details in the scenes such as the golden Buddha statues and the crosswalk. Using DiffusionLight, we can add 3D objects into the input image and relight them using our light estimate for seamless composition. Please visit diffusionlight.github.io for code and demo. Thank you.